The neutral wire and the ground wire serve distinct purposes within a residential electrical system. It is a misconception that the neutral wire is physically connected to the ground inside the circuit breaker box. Instead, the neutral wire connects back to the transformer's neutral point. This neutral point at the transformer is then connected to a grounding electrode, typically a ground rod driven into the earth. Similarly, the ground wire connects to the transformer's grounding terminal, which is also connected to the same grounding electrode. The power company delivers power to a residence through two primary conductors, a hot or phase conductor and a neutral conductor. The hot conductor carries the electrical current to the various circuits within the house, while the neutral conductor provides a return path for the current, completing the circuit back to the transformer. Without a neutral conductor, the electrical circuit would be incomplete and electrical devices would not function. The statement that the power company only delivers two wires, implying no neutral, is incorrect. A neutral conductor is essential for the operation of a standard residential electrical system. Now let's delve into the concept of phase angles. In a single-phase power system like the one typically found in residences in the United States, there's nominally only one phase. However, with the split-phase system that is common, the two hot legs are 180 degrees out of phase with each other. This means the voltage between the two hot legs is twice the voltage of each hot leg to neutral. This allows for both 120-volt circuits, using one hot leg and the neutral, and 240-volt circuits, using both hot legs. The 120-degree phase angle is typically associated with three-phase power systems, which are more common in industrial and commercial settings. Three-phase power systems utilize three separate conductors, each carrying an alternating current that is 120 degrees out of phase with the other two. This configuration provides a more consistent and efficient power delivery compared to single-phase systems. While it's possible that specific local configurations or older systems might deviate from the standard, the vast majority of residential power distribution systems in the United States operate with a split-phase configuration as previously described, where the two hot legs are 180 degrees apart. Now let's consider some practical aspects of grounding and bonding within a residential electrical system. Grounding refers to the intentional connection of metallic parts of the electrical system to the earth. This includes things like metal conduit, metal enclosures, and the grounding terminals of electrical receptacles. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, which in turn will cause a circuit breaker or fuse to trip, disconnecting the faulty circuit. Bonding, on the other hand, refers to the connection of all non-current carrying metallic parts of the electrical system together to create an electrically continuous path. This includes things like metal water pipes, gas pipes, and metal building components. The purpose of bonding is to minimize voltage differences between these metallic parts, which can help to prevent electric shock hazards. It's important to note that the neutral conductor and the ground conductor are intentionally bonded together at the service entrance, typically at the main service panel. This is the only point in the system where the neutral and ground conductors should be connected together. Connecting the neutral and ground conductors together at any other point in the system can create a dangerous situation known as a neutral ground fault. A neutral ground fault can cause current to flow on the grounding conductor, which can create a shock hazard. Now let's discuss some common misconceptions about neutral and ground wiring. One common misconception is that the neutral wire is simply a return path for current and that it doesn't carry any current under normal operating conditions. This is not true. Under normal operating conditions, the neutral conductor carries the unbalanced current from the circuits it serves. For example, if you have a circuit with two 100 watts lamps connected to it, and one lamp is turned on while the other is turned off, the neutral conductor will carry 100 watts worth of current. Another common misconception is that the ground wire is only there for safety purposes and that it doesn't carry any current under normal operating conditions. This is also not true. While the ground wire is primarily there for safety purposes, it can carry current under certain conditions, such as during a ground fault. In the event of a ground fault, the ground wire provides a low impedance path for the fault current to flow back to the source, which in turn will cause a circuit breaker or fuse to trip. It's important to understand the difference between the neutral and ground conductors and to ensure that they are properly installed and maintained. Improper wiring can create a dangerous situation and can increase the risk of electric shock or fire. If you are not comfortable working with electrical wiring, it's best to hire a qualified electrician to do the work for you. In addition to the topics already discussed, it's also important to understand the role of the grounding electrode system. The grounding electrode system consists of one or more grounding electrodes that are connected to the grounding conductor. The purpose of the grounding electrode system is to provide a connection to the earth, which helps to stabilize the voltage of the electrical system and to provide a path for fault current to flow back to the source. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The grounding electrode system must be properly installed and maintained to ensure that it is effective. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. The NEC is a set of standards that are developed by the National Fire Protection Association, or NFPA, and that are used to ensure the safety of electrical installations. The NEC is updated every 3 years, and it is important to stay up to date on the latest requirements. Article 250 of the NEC covers grounding and bonding. Section 250.24 covers grounding service supplied alternating current systems. This section specifies that the neutral conductor must be grounded at the service entrance. The grounding electrode conductor is used to connect the grounded neutral conductor to the grounding electrode. Table 250.66 in the NEC provides guidance on the size of the grounding electrode conductor. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Section 250.50 requires that all grounding electrodes that are present at a building must be bonded together to form a grounding electrode system. This includes metal water pipes, metal building frames, and concrete encased electrodes. Section 250.104 covers bonding of metal water pipes and other metal piping systems. This section requires that metal water pipes that are likely to become energized must be bonded to the grounding electrode system. Section 250.118 covers types of equipment grounding conductors. This section specifies the types of conductors that can be used as equipment grounding conductors. These include wire-type conductors, metal raceways, and metal armor cables. Section 250.130 covers equipment grounding conductor connections. This section specifies how equipment grounding conductors must be connected to equipment and to the grounding electrode system. The NEC also contains requirements for ground fault circuit interrupters, or GFCIs. GFCIs are devices that are designed to protect people from electric shock. GFCIs work by monitoring the current flowing in the circuit and by tripping the circuit if they detect a difference of 5 mA or more between the hot and neutral conductors. GFCIs are required in certain locations such as bathrooms, kitchens, and outdoor areas. The NEC also contains requirements for arc fault circuit interrupters, or SIs. SIs are devices that are designed to protect against fires caused by arcing faults. Arcing faults are faults that occur when electricity jumps between two conductors. SIs work by monitoring the current flowing in the circuit and by tripping the circuit if they detect an arcing fault. SIs are required in certain locations, such as bedrooms and living rooms. When troubleshooting electrical problems, it is important to follow safe work practices. Always turn off the power to the circuit before working on it. Use a voltage tester to verify that the power is off. Wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working with electrical wiring, it is best to hire a qualified electrician to do the work for you. Understanding the difference between neutral and ground, the NEC requirements for grounding and bonding, and safe work practices are all important for ensuring the safety of electrical installations. Remember, electrical work can be dangerous, so it's always best to err on the side of caution.